There are more than 100 billion stars in our Milky Way galaxy. Our sun is but one of these billions of stars. As we look out past our neighbors and beyond the edge of our own galaxy, we see billions and billions of other galaxies. It's the purpose of astronomers to study and understand the galaxies and the stars, and to understand the overall extent and structure of the universe. As we understand the present structure of the universe, we get evidence as to the origin of the universe, and ultimately as to the origin of mankind. And also this information allows us to look into the future and predict the destiny of the universe and of ourselves. I'm Karl Henize, astronomer and scientist astronaut. I'm the chief scientist, the principal investigator of Skylab Experiment S019, Ultraviolet Stellar Astronomy. The basic purpose of this experiment is to explore stellar spectra in the ultraviolet part of the spectrum. A spectrum is what an astronomer obtains when he sends ordinary starlight through a grating or a prism, which spreads the light out according to its color or to its wavelength. We have a diagram here of the overall spectrum that you might obtain from a star or a galaxy, extending all the way from the radio waves into the gamma ray region. It's one of the interesting things in nature that most of this radiation does not penetrate the Earth's atmosphere. Only very, very narrow bands do. For instance, this narrow band right here is visible light, which does penetrate the Earth's atmosphere, and of course it allows us to have the light from the sun that we use every day. In the radio region, there's again a rather narrow band that comes through the atmosphere of the Earth. But the very interesting regions of the infrared and the ultraviolet and the X-ray region is absorbed in the upper atmosphere and is not accessible to astronomers unless they go into space with their telescopes. On Skylab, we have a small telescope which will operate in space to obtain spectra of stars in this particular wavelength region. The particular stars that we'll study in this case are the very hot young stars called B stars. Let me show you in greater detail the types of objects and the features that we expect to see in these spectra. Here we have another spectral diagram in which we've plotted the energy curve or the brightness curve of the sun. The diagram runs from about 1,000 angstroms in the ultraviolet to 30,000 angstroms in the infrared part of the spectrum. Right here in the middle, you see the narrow band of visible light, which is transmitted by the Earth's atmosphere. You can see that the sun is brightest in the visible light range at about 5,000 angstroms. And as you move to the ultraviolet, it falls off very rapidly. In the infrared, it falls off but more slowly. Now, it's a well-known law of physics that the hotter any object is, the brighter it will be, the more radiation it will have in the ultraviolet part of the spectrum. That's true of the stars also. For example, the sun is a rather cool star that has a surface temperature of only 6,000 degrees on the absolute temperature scale, whereas the bright B stars that we're interested in studying on Skylab have surface temperatures on the order of 30,000 degrees. Let me draw a diagram here. The energy curve of the B stars peaks at about 1,000 angstroms. And here we see the general shape of the energy curve for the B0 stars. Which illustrates the fact that nearly all of their light, at least 80% of it, is in the ultraviolet wavelengths which can't be reached from the Earth's surface. A little of their light does come through the Earth's atmosphere, this little bit right here, so that we know they exist and we have some tentative idea of their nature. But it's obvious that when we reach this 80% of the light in the ultraviolet, we're going to understand these stars in much greater detail. At the present time, we suspect their temperatures is on the order of 30 or 40,000 degrees, but when we're able to study the fine spectral lines that we'll see in the spectra taken with Skylab, we're going to be able to be much more positive about the temperatures of these stars. And again, the temperatures of the stars lead us more to a story about their ages. It turns out that from what we know already, the B stars are extremely young stars, and this is because being hot, they radiate energy very rapidly. That is to say, they burn out their source of energy, their fuel, very rapidly. So the ones that we see must be very young. It turns out that we find them in groups in the Milky Way. And these groups are almost always associated with clouds of dust and gas. And it's to be inferred that somehow or other the clouds of dust and gas are condensing slowly but surely into stars, and that new stars are being born all the time. Here is an example of one of these gas clouds condensing into stars, which we know in the southern Milky Way. The large white area you see here is a cloud of glowing gas. You see fingers and filaments of dust in the foreground, which is blocking out the light that's coming from the gas cloud. Even though they can't be clearly seen here, there is a group of about 100 hot young stars which has condensed from this cloud of dust and gas. Now let's take a look at the telescope that we're going to use in Skylab. This is the Skylab instrument. The section that you see right here is the main telescope, and it comes itself in two sections. Here is the main optical system, which has a 6-inch mirror which gathers the starlight and focuses an image. The film magazine is this section here, and it contains 160 frames of special ultraviolet film. The section that you see up front here is called an articulated mirror system, or rather a periscope, to describe it more properly, because it has inside a mirror which can be, after the section is attached to the scientific airlock, and the airlock is opened, the mirror can be cranked out and then rotated and tilted in order to point around the sky at different star fields that we're interested in. This is illustrated over in this model. Here you see Skylab, and this is the orbital workshop area here. Here you see the crew quarters, and just above the crew quarters then is the major laboratory area. There are two scientific airlocks in this section. One is on the side of the sun, pointing out in this direction. The other one, the one which we use, is just at this position, pointing out away from the sun so that we can use it when the spacecraft is on the night side of the Earth. The astronauts operate this equipment entirely in a manual mode. The lever which you see here actuates the film advance system. Also, it opens and closes the shutter. The astronauts time the exposures by wristwatch, and the longest exposure we use is exactly 4.5 minutes. In initiating a cycle of operation with the instrument, the astronauts first have to assemble it and attach it to the scientific airlock. And as I said before, it attaches just at this flange to the airlock. Once it's attached, then the astronaut is able to crank out the mirror. And once the mirror is outside the hull of the spacecraft, then the astronaut is able to tilt and rotate the mirror to various positions in the sky. The fact that the astronauts almost completely operate all aspects of this telescope has several advantages. First of all, it allowed us to simplify the instruments considerably over what we find in the automatic observatories. This gives us much higher reliability in the equipment. Next, it gives us great flexibility, inasmuch as the exposure time is completely at according to the judgment of the astronaut or according to last-minute determinations from people on the ground. And finally, in building equipment of this sort, which is free of electronics and all sorts of automatic devices, we find that it's much more inexpensive than the equipment used on the larger automatic observatories. Another advantage is the fact that we can use photographic film, which has great advantages in high-resolution photography and also in wide-field photography. Here's a photograph taken with this instrument on the ground. Now, this gives you the idea that we are photographing not just one star at a time, but we are photographing perhaps more than 100 stars at a time. We have a field 4 degrees by 5 degrees on a side. Now, in this area of the sky, there are something like 100 stars, and therefore you see the spectra of about 100 stars on this one photograph. The smear that you see left-right in each one of these square blobs is the dispersing of the light of the star, the red, green, violet part of the star's radiation. This, of course, is only the visible light that gets through the Earth's atmosphere. On the bright star up here, we've illustrated how much further the spectrum will extend when we get into orbit with the instrument. Here you can see that the ultraviolet will extend all the way from this position all the way over to this position with all of the myriad of details that we're interested in studying in this star. In other words, here we have the 20% of the radiation which comes through the atmosphere. Here is the unknown 80%, which is going to give us the information we are interested in. The basic advantage that we get from photographs of this sort is that instead of looking at stars one at a time, stars that we already expect to be unusual or of importance to us, we're looking at all the stars that occur in this field. And as a result, we are making indeed a true survey in which we are able to make discoveries of stars whose ultraviolet characteristics are so unusual we were not even able to predict that they are special. These spectra will add new dimensions to our knowledge of star ages and star birth processes.